Hello there. Let's do one of these rotational equilibrium problems. So when we do rotational equilibrium problems, there are two conditions that need to be met. One, the net force has to be zero, right? So the sum of the forces has to be zero. That would be the first condition. The second condition is that the sum of the torques will also be zero. So just like when we did force problems, we sum up all the forces, we set it equal to zero. We'll do that for the first condition. And then for the second condition, we'll do the same thing and we'll sum up all of the torques. Okay, so there's two parts to these problems. We need two equations because there will be two unknown variables. So let me just read the problem that we're going to do and then I'll put it onto the screen. A uniform bridge, which is 20 meters long and it weighs 4 times 10 to the 5 newtons, is supported by two pillars located 3 meters from each end. If a 1.96 times 10 to the 4 Newton car is parked 8 meters from one end of the bridge, how much force does each pillar exert? Now this sounds terrible, it sounds awful, but we're going to find out it's not that bad because what happens is this is in rotational equilibrium. And so what we're going to do is we'll sum up the forces just like we normally have, and we'll sum up the torques. The object can't rotate because it's a bridge. We don't want the bridge to rotate. That would be bad for the bridge. But we're going to pretend that if it could rotate, where would it rotate around? Where is the pivot point? And we can put the pivot point anywhere. It doesn't matter. So we can put it anywhere on paper. And so one of the tricks that we'll do is we'll put the pivot point where one of the unknowns is. Why would we do that? Because if the pivot point is on a force, then that force cannot cause a torque. If you put the pivot point on a force on the pivot point, then that force cannot cause a torque. It's like you cannot open up a door, a swinging door, if you push on the hinge of the door. You have to push somewhere from the hinge outward to get the door to swing open. And so what that'll do is it'll eliminate one of the forces that could potentially cause a torque. Okay? So here's what the problem is. I'll put it on the screen so you can read it, and then I'll walk you through the steps for finding out the answer to this problem. All right, let's see if we can do this bridge problem then. I'm going to use the ruler here. Look at this. So what we'll do is we'll draw a picture of the bridge. Give ourselves enough room here. So this will be our long bridge. And for this particular bridge, we know that it's 20 meters long. So from end to end, 20 meters. And we know a few things about this bridge. It's a uniform bridge. So a uniform bridge means that the center of mass of the bridge will be right in the middle. So we're just sort of estimating here. So this will be the force of the bridge, the weight of the bridge. And it's pretty heavy, right? We've got 4 times 10 to the 5th newtons. And we know that there is a car that's parked on one side. And so I'll just put this here. This will be the force of the car. And it says that it's parked 8 meters from one end. And it doesn't matter what end that we put it on. You can put it on this side over here, or you can put it on this side over here. It really doesn't matter. I just chose to put it here. 1.96 times 10 to the 4 newtons. And it says that it was 8 meters from one of the ends. So this distance here is 8 meters. One of the keys for doing these types of problems is making sure that the diagram is pretty good. Since this is a uniform bridge, the center of mass of the bridge, FB, this number right here, would have to be right in the middle. So that means if the bridge is 20 meters long, then this would be 10 meters from one of the ends. It also said that we had 2 supports, and the supports were 3 meters from each end. And again, this is not drawn to scale, but I'm just going to put right here this would be, I'm going to call it F1, that's one of the supports, and we don't know that. And then on the other side over here, we have F2, and we don't know that one either. So the idea behind the bridge is that you have this bridge like this, and there's two supports here. And so these supporting places are pushing up, right? That's pushing up, and this one is pushing up, and that's what's supporting the bridge, and then the cars, they can drive back and forth across the bridge. So this sort of picture that I've sketched over here is basically the diagram that we have on this side. It said that these supports are 3 meters from the end, so this is kind of small, but I'm going to squeeze in 3 meters on both sides here. All right, you get the idea. Now, the key with this that we said is that because it's in equilibrium, you can put the pivot point anywhere. So I'm going to choose, because there's two unknowns, there's an unknown for this support and there's an unknown for this support, I'm going to put the pivot on one of those supports. I'm just choosing the left one, you could easily choose the right one. So if I put the pivot point here, right here, that means that this F1 cannot cause a torque. It's like pushing on the hinge of a door. You cannot get the door to open this way. You'd have to push somewhere along this lever arm. Now, because I put the pivot point there, then potentially what could happen, it's not going to happen, but it could, that the forces along this side could cause this to rotate. Like you could see that FC and FB, if they were allowed to, would cause the whole bridge to rotate around in this direction. Right, these forces here would cause it just to swing around. And then F2 would cause it to rotate in this direction here. Well, if I rotate in this direction, which is counterclockwise, this is a positive rotation, so F2 would cause a positive torque, and FC and FB would cause counterclockwise, clockwise, which is a negative rotation. So here's our diagram. Now, what we want to do is we want to do two things. We want to sum up all the forces, and we also want to sum up all of the torques. So if I were to sum up all of the forces, wrong color, let's go back to this color. If I were to sum up all of the forces, and really they're on the y-axis, but because there's no lateral forces, I'm just going to put the net force. Then which ones are pointing in the positive direction? Well, F1 is pointing up, F2 is pointing up, those are positive, FC is pointing downward, and FB is pointing downward. And because we're in equilibrium, we set that equal to 0. And then all we need to do then is look at this here. The forces that are summed up, we have all of them except for F1 and F2. But since F1 is where the pivot is and it cannot cause a torque, I'm going to solve this equation for F1. So F1 equals, I'll just have to add FC and FB, so the weight of the car plus the weight of the bridge minus the other force, F2. And it's this equation, which will be part 2, will solve and give us for F1. And if I had F2, then I could certainly use this equation and I would be done. I would be able to finish the problem. So the first condition is met, right? The first condition, we have this problem met. Now the second condition is we need to sum up all of the torques. So how do we do that? Well, what I'm going to do is I'll just write it out the same way. I'm going to add all of the torques. And so to add all these torques, I'm going to start with the positive torques. So remember, torque is FD. I'm not going to worry about the sine theta because all of these forces are perpendicular to the lever arm. So all I need then is the force, and I need to know the distance, which is the lever arm. And I can get those distances because I already have them all measured out over here on our diagram. So if we start with the positive torques, the only one that causes a positive torque is F2. Well, what's the distance from F2 here all the way to my pivot point? Because that is my lever arm. Well, that would be 14 meters. So it would be F2 times 14 meters. That's the torque for F2. I've got two negative torques. So So let's just keep let's just keep working down our lever arm. So the next force that we come to is FB. That's a negative torque, so I'll write minus FB. And what is the lever arm for FB? Well, it's this distance to our pivot, which is 7 meters. And then I have one other one, right? I've got FC over here. That's also going to cause a negative torque. So FC. And then what is the lever arm right here? Well, that one would be 5 meters. Let me just make this a little neater. This is an M. And because it's in equilibrium, we say that this is equal to 0. Now, I don't have to worry about F1 causing a torque because it's at the pivot point. So I've eliminated F1 as one of the options for causing a torque. If I had put the pivot point here on F2, then I would have eliminated F2 as a force that would cause a torque. My lever arms would change, but I'd still end up with the same solution. I would still be able to find what F1 and F2 are equal to. If I look at this part right here right now, then you can see that you have everything except for F2. So if I take this side and I solve it for F2, I can add this to the other side, this torque for FB. I can add this to the other side, and then I'll divide by my 14 meters. So the solution to this one would be FB times 7 meters plus FC times 5 meters divided by our 14 meters. And this will give us F2. Once I have F2, I can then find F1. So let's put the numbers in now. So F2 equals, well, FB was 4 times 10 to the 5th newtons. The lever arm was 7 meters, plus FC was 1.96 times 10 to the 4 newtons. The lever arm is 5 meters, and I divide that by 14 meters. F2 equals all the calculator stuff that you can do. I have 2.07 times 10 to the 5th newtons. So that is the support right here on the side that doesn't have the car. If you chose to put the car on the other side, then F1 would be equal to this. You'll still get the same numbers, it just depends on how you set up your diagram. Now that we have F2, we can simply use our first equation that we generated, and we can find what F1 is equal to. FC, 1.96 times 10 to the 4 newtons plus 4 times 10 to the 5th newtons minus our newly found F2, 2.07 times 10 to the 5th newtons. And then I just combine those and I get 2.13 times 10 to the 5th newtons. And there we have it. We've got our two unknowns. We needed two equations because we had two unknowns. We used summing of forces to find one of the unknowns. We summed up the torques to find the other unknown. So these can be kind of fun to do. There's usually two parts to these problems. That's how we do this one. And it's actually one of the problems that's on the worksheet that was assigned. Give it a go and let me know if you have any questions.